Well, hey everyone, and welcome back. This video is going to be more theoretical rather than applicable or experimental, as many of my previous videos have been. What I mean is that this is dealing with mostly stuff that's just good to know and keep in your head, rather than showing or explaining concepts that you'll be using on actual, say, geologic maps. So it's a bit of a change of pace, but I wanted to give a overview of everything that has to do with Earth's crust in this video. And just for a brief, very brief review, if you aren't aware, the Earth is divided into layers. And the innermost layer is the inner core. That's right here. Inner core, which is just a sphere, a very hot metal in the middle of the Earth. I'll go into more detail on these other layers in later videos, but for now we're focused on the crust. Then there's the outer core, which is a liquid spherical shell that outlines the inner core that is responsible for generating our magnetic field. Then we have the mantle, which is a semi-solid or plastic sort of layer that's constantly flowing and in motion, responsible for the movement of our tectonic plates. And then this very thin outer layer we have is the crust. So we're going to be focusing on the crust. And although I drew this circle diagram up in about 10 seconds, I wasn't focused on being exact or artistic. You can see that the crust is a very small, compared to the other layers, it's incredibly thin. And that is true in almost, that is true to the actual Earth itself. The crust makes up about, I'll start writing down some facts here. Hopefully you've got this image in your mind. The crust makes up about 1% of the Earth's total volume. That is just a tiny, a tiny sliver of the entire volume, and it's amazing to think that, even the deepest points we've ever traveled in the Earth have still been in the crust. Obviously, humans aren't built to survive the high temperatures of the deep, deep crust or the mantle. Continental crust is generally between generally between 30 and 50 miles deep or thick. Compared to oceanic crust, which is generally 5 to 10 miles deep. So one of the things you'll notice right away is that continental crust is quite a bit thicker than the oceanic crust. There are some key differences between continental crust and oceanic crust that we can detail. Aside from just their depth, continental crust is usually I guess I'll changing my format a lot here. We'll have continental and oceanic, just for a quick comparison. So yeah, we already have the 30 through 50 miles compared to the 5 through 10 miles. But then there's also other things, such as the continental crust is generally granitic in its composition, coming from the word granite, and this is generally, oceanic crust is generally basaltic in its composition, coming from the word basalt. Continental crust is on average around 2 billion years old. On average. Obviously, at some of the deepest points it's much older. At the very surface there can be much younger rock, but that's on average. And similarly, the average for the oceanic crust is only 200 million years old. So just comparing these numbers, continental crust is on average 10 times older than oceanic crust. And finally, I don't have specific numbers in mind for this, but continental crust is more dense, less dense than oceanic crust. And oceanic crust is more dense than continental crust. So oceanic crust is thinner, but it's also more dense. So if you took a chunk of continental crust and a chunk of oceanic crust, then the oceanic crust would be heavier than the continental crust. If they were of equal size, that is, equal volume. And those are the main differences between the two, and those give you a generally good idea of how the crust works. Some other facts. The crust in the upper mantle meaning the very, very top of the mantle, which we'll get into this in the next video, but the upper mantle is also rigid, much more close to being fully solid than the rest of the mantle. As I said earlier, most of the mantle is very plasticky, and it allows for convection currents which drive our plate tectonics. So the crust in the upper mantle are part of what is known as the lithosphere. Which overlies the asthenosphere. Nothing too important about that. I'm not going to jump into facts about the lithosphere right now, but just know if you ever hear that term, that's what they're referring to. As far as temperature goes in the crust, the temperature gradient is usually roughly, for every 1 kilometer you travel downwards, for every 1 kilometer distance you travel, it'll increase by about 30 degrees Celsius. So you'll go up 30 degrees Celsius for every kilometer you travel. That's an average, and it's mostly applicable to the upper regions of the crust. Obviously, we haven't traveled down to some of the even lower parts, but needless to say, the gradient does increase from 30 gradually as you go deeper and deeper into the crust. And it starts off lower than 30, obviously. The temperature of the crust at its boundary with the mantle, so right between the two, at the mantle, where it makes contact with the mantle, is generally between 200 degrees Celsius and 400 degrees Celsius. Somewhere between there.